Okay, welcome folks. So we're looking at Unit 7, final exam review. A couple of comments just about the key terms up on top of the assignment here. One thing to keep in mind that will relate to some of the skills, this thing called an empirical formula. That's what we call the simplest ratio of atoms or ions that make up a compound. That's a little different than something called its molecular formula. And its molecular formula relates to what the actual ratio would be. Just to give you a, for instance, example, what we mean by this, glucose has a molecular formula, C6H12O6, right? That's the real ratio. The simplest reduced ratio, called the empirical formula, is CH2O, right? They can each be reduced by a value of 6. So carbon reduces to 1, hydrogen reduces to 2, oxygen reduces to 1. And what we call these then, right, the actual formula is called the molecular. The simplest reduced version of that formula is called the empirical. Sometimes the molecular formula can't really be reduced because it's already in a simplest form. And then we just call it the empirical formula as well. So quick reminder about a few items that will relate to ideas. I did notice this item right here where it says formula unit. The word atom appeared on here twice. The intention was to make certain that we understand there's a particle for ionic compounds, and that particle is never called molecules. Remember, ionic compounds are compounds that begin with a metallic element typically. So if we have a metal bonded with a non-metal or a metal bonded with some other kind of ion, we typically call the particle of that compound a formula unit, never a molecule. Okay, let's get right into the skills now. So this particular question is asking for us to calculate the formula mass and the percent composition. Well, formula mass comes from the chemical formula. Here's the chemical formula, 1 barium, 2 fluorine. So what we did is we kind of took inventory over here. There's 1 barium, there's 2 fluorine. We looked at the periodic table. We said for every 1 barium, there's a mass of 137.33. For every 1 fluorine, a mass of 19. So we multiply the quantity times the mass, and we get a total contribution from each element. We add that up, and here in pink, we have the formula mass. The formula mass is the whole that we compare the parts to. So the part out of 175.33, only 137.33 comes from barium. And out of that, only 38 of that comes from fluorine. And that's how we turn this into percentage then. The part from barium compared to the whole amount, the formula mass, times 100, 78% barium. We do the same thing for fluorine. Right, part divided by whole, 21% fluorine. Okay, moving forward, we got a couple of special chemical substances called hydrates. Hydrates just mean that there is water attached to an ionic compound. So we take the name of the ionic compound and we write the formula like we normally would. Copper 2 sulfate comes from 2 ions, right? The copper 2 ion, which is +2 charge, and the sulfate ion, which is -2 charge. So we see that the +2 and the -2 cancel each other out. CuSO4 would be the symbols for the formula for the ionic compound. And then the hydrate, well, look, this says this is a pentahydrate, which means there are 5 water molecules loosely attached to this. So dot 5H2O, and we have the chemical formula. Likewise, below there, barium chloride. Right, there's the ionic compound. We look at the charges. Barium's a +2 charge. Chloride is a -1 charge, right? We're using our ion chart for this. We crisscross the charges. It would require 2 chlorine, 1 barium. So barium chloride, BaCl2, and then the hydrated piece of it, dihydrate, really just means 2 water attached. So dot 2H2O. Lastly, calcium nitrate, right? Calcium ion +2 charge, nitrate ion -1 charge. So we need 2 NO3s and 1 Ca, which is what we have here. And then we call this a tetrahydrate. Tetra is the prefix that represents 4.4H2O. There we go. That's our ideas that relate to naming hydrates. Number 3 is actually related to this percent composition idea. So it says we have a chemical compound called lead 2 oxide, and we have 245 grams of it. What this is asking us is how much lead is making up that 245 grams of the total compound. So basically, if we know the percentage of lead, we apply the percentage to this 245, and we know the exact mass of lead that is found in that 245 grams. So once again, we went back to the process. 1 lead, 1 oxygen. We looked up the atomic mass, 207.2 for lead, 16 for oxygen. Since there's only 1 of each, we add that up. We don't have to multiply anything in this case. The whole amount is 223.2. The part that comes from lead is 207. 207 divided by 223.2 times 100. We get a chemical we know is 92.8% lead. What we then do is we take 245, right, the mass in the chemical substance, a total mass 245. If 92.8% of that is lead, we multiply 245 by 0.928, and we get 227 grams of lead as a result. Question 4, really just some factual ideas. These facts really need to be owned to be able to deal with chemical quantities. How many particles are equal to 1 mole? Particles is always this thing, Avogadro's number, 6.02 times 10 to the 23rd. What gas volume is equal to 1 mole when the gas is at standard temperature and pressure? That's always this amount, 22.4 liters. So those are factors that we should commit to memory. And then lastly, why does the mass equal to 1 mole? We call that the molar mass. For any substance vary from the amount for any other substance, and it relates to the formula. No 2 substances are made of the same ratio of elements, and perhaps not even made of the same elements. So it's based on the unique formula that every chemical substance owns. For example, carbon dioxide has a molar mass that's different than water because carbon dioxide is made of a ratio of carbon and oxygen. Water is made of a ratio of hydrogen and oxygen. Okay, and item 5, we get back to some skills. Most of you are probably using what you see on the left side. So I'm going to make a comment about what you see on the left side and just make you aware that the same calculation was done with a different procedure on the right side where I'm drawing these arrows. On the right side, this is that process called dimensional analysis. And a few of you are using that. It's a great strategy, very organized. It uses canceling units. Grams cancel, it leaves mole. If you're not using that, let's go back to what many of us are using. Many of us are using this strategy called proportion method. And when we use proportion method, I said the best way to think about that, we read the words and there's a given amount, and we read the words for the desired amount. So there's always a given and a desired, and we make a fraction out of that. We put the given amount over the desired amount to get started. So in this first example, what we're looking at is the given amount from the words, 32.8 grams of ammonia, NH3. The desired amount says, hey, how many moles is that? So X, how many? That's the unknown. So given over desired on the left. On the right, we put the factors that allow us to deal with the quantity conversion. So since this is a mass, the molar mass is equal to 1 mole. We get the molar mass by looking at the formula, 1N, 3 H's. 17.04 grams is equal to 1 mole. We cross multiply 17.04 times X, 32.8 times 1. We get a formula. We solve for X by dividing each side by what's attached to it, 17.04, and we get 1.92. So it's all about organizing given over desired. And then on the right side, the factors equal to 1 mole, or whatever quantity is equal to 1 mole, that's what we fill in on the fraction on the right side using the same units. So if we look at part B, look at, we're given a mass amount of carbon dioxide. It says, hey, tell me what the volume is of that if it were at standard temperature and pressure. So we take the given 27.6 grams over the desired X number of liters. On the right side, we put the quantities equal to 1 mole. Well, 1 mole of carbon dioxide, based on its formula, called the molar mass, is 44.01 grams. 1 mole of volume is always equal to 22.4 liters, as long as it's at standard temperature and pressure. What we do next is we cross multiply, right? We get a formula, 44.01x is equal to 618.24. Divide each side by what's attached to x, 44.01. We get 14.1 liters. Moving on to example C. Example C is a particle amount. Well, that doesn't matter. We just use the particle quantity equal to 1 mole. So the given amount, 9.07 times 10 to the 23rd formula units. That's a special kind of particle. It says how many moles, so our unknown is x, given over desired. On the right side, we organize, right? The quantity is equal to 1 mole. Well, if it's particles, it's always 6.02 times 10 to the 23rd, right? On the bottom, because it says mole, we just put 1 mole. We cross multiply, we get a formula. 6.02 times 10 to the 23rd x is equal to 9.07 times 10 to the 23rd. We divide each side by 6.02. Don't forget the times 10 to the 23rd, right? And we'd end up with 1.51 moles. Just be careful how you use your calculators. If you're using your calculator, you'll probably want to put 6.02 times 10 to the 23rd in parentheses and 9.07 times 10 to the 23rd in parentheses to avoid what we call order of operations errors. Okay, letter D, there's a relationship between volume and mass. So it says what mass? Unknown mass, grams. Volume, 32.2 liters, given over desired. On the right side, the quantity is equal to 1 mole, 22.4 liters, 88.07 grams. That's from 1 sulfur and 2 oxygen. We cross multiply. That turns it into a formula, not a formula, an equation. 22.4x is equal to 2063 and change there. Divide each side by 22.4. You'll get an amount in grams, 115 grams of sulfur trioxide. Letter E is asking for a mole amount. So given is liters, a volume. Desired is X moles. So we put the quantities equal to 1 mole on the right. 22.4 liters is the quantity equal to 1 mole when it's volume. 1 mole on the bottom. Cross multiply, right? 22.4 times X, 88.2 times 1. Make an equation out of it. Divide each side by 22.4. And you get a value of 3.94. Okay, so let's move forward. Give you a little bit of a quick mini lesson here. There are 3 different kinds of particles. One of those particles is called atoms. Another would be molecules. Another would be formula units. So we worry about what chemical type we're speaking about. We're either speaking about elements or we're speaking about compounds. So when we look at a particle type, it depends what the chemical substance is. Well, copper is an element. So most of the time when we speak about elements, the particle is called atoms, right? There are sometimes some exceptions to that, but in this case, copper makes or is made up of what we call atoms. So we'll highlight when that is not the truth in a moment. So if we look at the example, the next one, carbon monoxide, that's not an element, that's made of multiple elements. So that's a compound. So when it's a compound, we're either going to call the particles molecules or we're going to call them formula units. We're going to call them molecules when they are covalent bonded, meaning they start with a non-metal element like carbon monoxide does. Carbon's not a metal, so we call that a molecule. If you look at the example below there, the chemical starts with a metallic element, sodium nitrate. That's a compound beginning with a metallic element. Those don't make molecules, those make formula units. Example below that, sulfur hexafluoride, a compound begins with a nonmetal, the nonmetal sulfur, we call those molecules. And then this last idea, nitrogen, notice nitrogen is 2 ends joined. So we said that sometimes elements can't be called atoms, sometimes elements have to be called molecules. And that's those elements that end in gen or ine. Nitrogen, right, is always diatomic. 2 atoms of nitrogen joined, we call those molecules all the time. So elements that end in gen or ine, like nitrogen, right, we call those molecules. Number 7, there's a strategy. The strategy uses a little bit of a rhyme. The rhyme we used in class. My name is Chem Shady. No. So what we look for is we look for this rhyme, right? We look to use this or apply this. So if we're asked to calculate an empirical formula, here are the rhyme. Percent to mass, mass to mole, divide by small, multiply till whole. Basically means take these percentages and just change the label. Get rid of percent, change them to gram. That's all we did down here. Grams of carbon, grams of hydrogen, grams of oxygen. Okay, so that's percent to mass, right? That's this step, percent to mass. Next step, mass to mole. Well, we take the mass of each element and we just divide by its molar mass. For carbon, it's 12.01. For oxygen, it's 1.01. For hydrogen, it's 1.01. For oxygen, it's 16. So 26.45 divided by 12.01, we get 2.2. 3.3 divided by 1.01, we get 3.27. 70.3 divided by 16, we get 4.39. That's mass to mole. Now we got 3 mole amounts, percent to mass, mass to mole. Divide by small, that's the next step of the rhyme. We take the smallest mole amount and we divide each of them by that. What we're guaranteed to do is we're guaranteed to get a whole number 1 when we do that. And we're looking to try to get whole numbers by doing this. And I said in class, we want to look for the numbers that we get. If the numbers that we get are not within 1/10 of a whole number, then we apply the last step, multiply till whole. So we got 1, 1.49, and 2. 1.49 is not within 1/10 of a whole number. So we multiply by some value to see if we get something that is super close to a whole number. So when we multiply, super close again means within 1/10. When we multiply 1.49 times 2, we get 2.98, which is essentially the value 3. Just remember, I multiply each of the mole amounts by the same whole number. So in this case, 2 worked, and we get a ratio of 2 to 3 to 4, C2H3O4. That would be the empirical formula. Letter number 8, excuse me. Number 8 really just says, hey, listen, if the formulas are related by some whole number, their masses are also related by a whole number. Remember, there's something called the molecular formula, the real ratio, something called the empirical formula, the simplest reduced ratio, like we calculated in number 7 above. So if we know, based on the words, that they give us the actual molar mass for the compound, this right here, and they give us the empirical formula, what we do is we calculate the mass of the empirical formula. Sometimes I call that EFM. So we make a ratio, the mass of the actual chemical formula, called the molar mass, and the mass of the empirical formula. And we do that by division. 70 divided by 14. We essentially get a whole number by doing that. That whole number is the multiplier that we apply to the empirical formula. The empirical formula is CH2. So the empirical and the molecular formula are related by the number 5. So CH2, we multiply each part of it by 5, and we arrive at C5H10. We won't worry too much about number 9, but number 9 is really just a marrying of what we did in number 7 and number 8 together. That's probably a little too complex than we have time for on exam day. So don't stress too much about item 9. And I hope you found this useful for reviewing our Unit 7 about chemical quantities. Until the next time, this is Mr. Brewer. Thanks for listening.